Here on Earth, our intuition for distance is built entirely around human speeds. A long trip is a 5-hour flight. A vast distance is a multi-day road trip. But as we leave Earth's atmosphere, those metrics immediately struggle. Take our closest celestial neighbor, the Moon. It sits about 384,000 kilometers away. If you were to drive a car toward it at a constant highway speed, it would take you over 160 uninterrupted days to arrive. The next marker, the Sun, forces us to upgrade our metric to the speed of a commercial jet to even make sense of the distance. Even flying steadily at 900 kilometers per hour, it would take you 19 years to reach the Sun. If you pointed that same commercial jet toward Mars, when it is on the opposite side of the solar system, you would be flying for upwards of 50 years. And those are just our immediate planetary neighbors. If we look outward to the closest star system to our Sun, Alpha Centauri, human travel times fail completely. A spacecraft moving at 17 kilometers per second, roughly the speed of our fastest probes, would take over 70,000 years to reach it. Because our scale of speed breaks down the moment we leave our solar system, we can only grasp the true size of the cosmos by examining the absolute limits of human reach. The furthest physical horizon humanity has ever reached is embodied by the Voyager 1 space probe. Launched in 1977, it has been drifting continuously into the void for over 4 decades. In 1990, at the suggestion of the astronomer Carl Sagan, engineers commanded the probe to turn its camera around and take one final photograph of its origin point. From a distance of 6 billion kilometers, Earth registered as a faint, pale blue dot, a fragile single pixel suspended in a vast black sea. Yet, as far as Voyager 1 has traveled, it is nowhere near the solar system's edge. The true physical boundary is thought to be the Oort cloud, a massive shell of icy objects extending up to 1.9 light-years wide. Here, we measure by the light year, the distance light travels in a single year. Despite traveling at immense speeds for most of modern human history, our furthest physical envoy is still just on the cusp of interstellar space. It hasn't even breached our own solar neighborhood. To measure the Milky Way galaxy, which spans roughly 100,000 light-years in diameter, the light year becomes our only practical unit. This map visualizes our galaxy from the top down. If we zoom in thousands of times to this microscopic glowing dot, we find the human radio bubble. This 100 light-year sphere marks the absolute farthest extent of our broadcasted presence in the cosmos. The outer boundary of this bubble is made of our earliest television and radio broadcasts. Those signals have been expanding outward at the speed of light since leaving our antennas. The Milky Way holds hundreds of billions of stars. But for any star system outside this exact 100 light-year sphere, our signals simply haven't arrived yet. To them, humanity is completely undetectable. The entirety of our recorded human history exists solely inside this tiny bubble. Beyond it, we are merely a whisper in the cosmic wind, completely unknown to the vast majority of our own galaxy. Leaving the Milky Way entirely, we enter the silence of intergalactic space. Our galaxy floats within a localized cluster of about 50 other galaxies, spread across 10 million light-years, known as the local group. But even that massive cluster is just a minor component inside the Virgo supercluster, a structure encompassing over 100 galaxy groups stretching across 110 million light-years. This 3D web maps the ultimate architecture of our cosmic region, the Laniakea supercluster. Extending over 500 million light-years, it contains the Virgo supercluster, along with countless others. Laniakea holds the mass of 100 million billion suns. All of its thousands of galaxies flow like streams of light toward the Great Attractor, a mysterious, dense gravitational nexus pulling everything towards its center. At this scale, Earth, our Milky Way, and our entire local group are reduced to microscopic threads woven into a gravitational network far larger than human comprehension. There is one final boundary, the limits of the observable universe. The absolute furthest distance we can detect stretches about 93 billion light-years in diameter. This measurement presents a mathematical paradox. Science dates the universe at 13.8 billion years old. Since nothing travels faster than light, The observable universe should theoretically have a maximum radius of 13.8 billion light-years, yet we know it measures 93 billion across. This grid illustrates how that is possible through cosmic expansion. Since the Big Bang, the physical fabric of space itself has been stretching. The distance between celestial bodies is actively increasing over time, pushing objects farther and farther apart. Because of this stretching, distant regions of space are currently expanding away from us faster than the speed of light. The light from those galaxies will never be able to cross the expanding gap to reach our telescopes. As those distant galaxies cross our visual horizon, they retreat permanently into the dark. We will never know the true size of the cosmos, but knowing that infinite wonders are steadily fading from our view makes the preservation of our tiny, isolated, pale blue dot all the more vital.